This video is discussion on Lab 12, which is Charles' Law. All right, so it's a continuation of the gas laws, and Charles' Law is dealing with the temperature volume relationship. So in this case, pressure as well as moles of gas are kept constant, and you find that there is a direct relationship between the volume of an ideal gas and the absolute temperature or the Kelvin temperature. Remember, gas laws, anytime you do any kind of problems in gas laws, make sure you convert the temperature from degrees centigrade to Kelvin, right? So Charles' law takes the form V1 divided by T1 is equal to V2 divided by T2. Now, another way to rewrite this is opposites. So if I have V1 times the T2 equals V2 times the T1, it's much more convenient because you can solve for an unknown temperature or volume when you have that in that kind of form. So here we're going to take another Erlenmeyer flask in this experiment 1, and you're going to fill it with 1.5 atmospheres of the methane gas. Click on the flask to close it, and then attach a syringe so that some of that gas will flow into the syringe. When this happens, the pressure of the gas inside the flask and the syringe would be a constant at 1 atmosphere. Remember, pressure has to be kept constant, and so does moles of gas. And since you're having a closed environment, you're able to keep the moles of gas constant as well. Now then, you're going to attach a thermometer to this flask. Click on the setting of the thermometer till it turns to K, which is Kelvin. So the total volume of the gas is going to be the 150 ml of the flask plus the 75 ml from the syringe, because remember, gas spreads, and so the volume of the gas is the volume of the total volume of the cylinders in which the gas, or the total volume of the containers rather, in which the gas is present, right? So your initial volume is 225 ml for methane gas. Record the room temperature, which is 21.5, but here remember we're going to look at the recording in Kelvin, so 294.6 Kelvin. Now you're going to place it in a constant temperature bath set to 0 degrees centigrade. So 0 degrees centigrade is 273 Kelvin, all right, or 273.1 Kelvin to be more precise. So you'll record the total volume of the flask and the syringe at this temperature. Okay, so you went down from the room temperature to 0 degrees. So room temperature was around 21.5 and the equivalent was 294 Kelvin, and you came down to 273, and therefore, because there's a direct relationship between pressure and between volume and temperature, as the temperature goes down, the volume will also decrease. So here the volume at 273 is going to be less than the volume at 294K. And then once you make a record of that volume as well as the temperature, the corresponding temperature, then increase the temperature to 40 degrees centigrade, which in Kelvin is 313.1 Kelvin. Now record the new total volume, which should have gone up. then increase the temperature again to 60 degrees, which is 333.1 K, and then record that new volume, which again would go up, and then repeat this process for 80 degrees centigrade, so 353.1 K, and again at 100 degrees centigrade, and record the volumes at both those temperatures. In experiment 2, you're going to take another Erlenmeyer flask, add 1.5 atmosphere butane gas, close it, attach the syringe, let some of the gas flow into the syringe so that the pressure stabilizes and remains constant at 1 atm. Attach a thermometer, set it to Kelvin, and again the total volume of the butane gas is going to be 225 ml. Record the temperature, room temperature, which is 294.6 Kelvin, and then increase the temperature. So you're not taking a 0 degree centigrade measurement because of the fact that butane, unlike methane, will condense. All right, okay, so you cannot take a measurement at 0 degree centigrade. So you'll simply increase that temperature to 40 degrees centigrade or 313.1 K, record the volume, and go on to 60 and 80 and then 100. All right, so the only data point that is missing is the 0 degree centigrade measurement. So we talked about why we need to have that syringe. It's because you want to equalize the pressure inside the system and outside of the system, the outside system being the surrounding air, which is at 1 atmosphere. Okay, so you want to keep that air pressure or the gas pressure constant. So the data for experiment 1 is, as you can see here. All right, so you can see that this data point should have been here rather than here. So as you can see, as the volume increases, you can also see that the temperature is gradually increasing. All right, so you can see that it goes from 273 till to 373, 100 degrees centigrade, and the volume is steadily rising from 208 to 285. So now in this case, you don't have to do one by anything. You can simply plot volume versus temperature being on the x-axis, and you'll get a straight line. All right, so Charles' law, you're going to get a straight line just by plotting the volume versus temperature. Okay, so the temperature is in Kelvin, and they are asking you to determine what the volume would be at 50 degrees centigrade. Now 50 degrees centigrade, if you do the conversion, is 323.1 Kelvin. And so when you draw perpendicular up to the plot and then another line to the y-axis, that corresponds to around 246 mil. Okay. Now I didn't get it off this graph. Obviously, I just plugged it into the equation for Charles' law, and I actually calculated this number, and you can do that as well. So again, 393.1 Kelvin. If you see what the corresponding volume is, it's around the 300 mil. Okay, this is not accurate enough, and so when you do the calculation and the math, it should come out to be around 300 mil. Okay. All right, this is the data for experiment 2, and again you can see that the only data point that is missing is the 0 degrees centigrade. So you can see that as the temperature increases from 294 to 373, so does the volume, and the numbers look exactly the same to methane. And so does the plot. And here they're asking you, since we didn't have a data point at 0 degrees, they're asking you to get it off the plot or by calculation. And so 273.1 K, the corresponding volume is slightly above 200, so about 209 mil. And then 70 degrees, which is 343.1 K, and that is slightly above the 250 mil mark, and that's 262 mil for the butane gas. So the aim of this experiment was to determine the relationship between volume and temperature for methane and butane. So I predicted that for both gases, just because as you increase the temperature, they're both ideal gases, and as you increase the temperature of an ideal gas, the gas particles become more active, so they expand, and so the volume should be gradually increasing, right? Showing the direct relationship between volume and temperature. You write a listing of the materials and equipment used, write down your procedure as you perform the graph, and then mention the fact that you did not take a 0 degree data point when you are writing the procedure for experiment 2. Okay. So what are some of the observations? The volume was gradually increasing from 208 for experiment 1 and 225 for experiment 2 up till 285. Okay. The volume versus temperatures were straight line plots for both gases, showing the direct relationship between volume and temperature. The results refer to the data and the graphs. They're identical for both gases, showing that both obey Charles' law. Okay. So Charles' law states that for an ideal gas, volume and temperature are directly related, provided pressure and moles of gas are kept constant. So the conclusions, the results indicate that both gases are behaving identically, they are both ideal, and they obey the Charles' law, and the straight line graphs confirm this direct relationship. So, of course, my hypothesis was supported. The implications of Charles' law in everyday life is, for example, if a can of soda bursts on a really hot day, it's because of the increased temperature inside makes the gas, which is carbon dioxide, expand. And then since it's a closed container, the pressure builds up so high that the can will burst. So how is this important? For example, if you're going to be storing or handling gases which are in closed containers, and as you know that especially in hospitals for anesthesia, you are using gases and they come in these containers, so proper precautions need to be maintained for controlling temperature during both the transport and the storage. And other real world examples is like a balloon either shrinking if you place it in a freezer, and I'll have to stop over here.